Hello, welcome back. Let's talk about the chain rule, section 11.4. I do have, if you need a review of what composition of functions is, what composition of functions consists of, I have a handout that will allow you some extra practice. I will throw it up on Blackboard I'll put it up on Blackboard and link it in this video. I really should write that down. I'll do it though. Let's talk about the chain rule. All right, one rule, plenty of examples. Here we go. If f is a differentiable function of u and u is a differentiable function of x, then the composite f of u is a differentiable function of x, and the derivative of f of u is f prime of u times du dx. So in words, the derivative of f of something is the derivative of f evaluated at something multiplied by the derivative of, quote, something. Or if we think about f as a composite function, right? Instead of using u, let's use it as a function form g of x. If I want to find the derivative, it's the derivative of the outside, where we leave the inside alone, and then we multiply by the derivative of the inside. All right? Derivative of the outside, leaving the inside alone, times the derivative of the inside. All right, and here are my words. This is what I will use frequently, but you could also think of it as a dy du du dx. Here we go. If this were a composition, right, a composition of two functions, I would say that the inside function is 3x minus 1, and that the outside is something squared, right? So if you were to evaluate this, you would find the 3x minus 1 part first, and then you would square. So I'm going to make the outside square, and the inside is what's inside there, 3x minus 1. Here's how I use my derivative. The overall derivative is the derivative of the outside. Something squared has derivative 2 parentheses to the 2 minus 1, right? 2, leave the variable alone, subtract 1 from the exponent. All right, so that's the derivative of the outside in green. Now it says leave the inside alone. So I'm going to put 3x minus 1 back inside those parentheses. And then I'm going to multiply by the derivative of the inside. Derivative of 3x minus 1 is 3. Okay, so derivative of the outside, here in green, 2 parentheses to the 2 minus 1. Leave the inside alone, multiply by the derivative of the inside. 2 times 3 makes 6. 2 minus 1 is an exponent, makes a 1 exponent, so 3x minus 1 has an exponent of 1. 6 times 3x minus 1 gives us 18x minus 6. All right, let's do it again. I'm going to change my marker color here real quick. F of x is 1 minus x to the negative 1. On the inside of the parentheses, inside of a radical, inside of a denominator, there's a lot going on, right? There's a lot of different places we could think of as inside. Inside is 1 minus x. What is it inside of? It's inside of to the power of negative 1. Well, this is just kind of a generic power rule, and the derivative of outside, the derivative of something to the negative 1, is bring down the negative 1, leave parentheses, subtract 1 from the exponent. So derivative of the outside, here in green, leave the inside alone, and then multiply by the derivative of the inside. All right, derivative of 1 is 0. The derivative of minus x is negative 1. So we have negative 1 times negative 1 is 1. Negative 1 minus 1 is a negative 2. And frequently we just don't write that 1 as a coefficient, or we might write it as 1 over 1 minus x all squared. This one's fine. This one's absolutely legit too. Either way is all good. Number 3, if f of x equals 4x plus 7 to the negative 2 power, it looks to me like 4x plus 7 is inside. What is it inside of? It's inside of this negative 2 exponent, right? Something to the negative 2 power. Well, the derivative of the outside is negative 2 parentheses to the power of negative 2 minus 1. Derivative of the outside, awesome. Leave the inside alone, so 4x plus 7, the inside is exactly as it's written. And then times the derivative of the inside. Derivative of 4x plus 7, it's a linear function, has slope 4. Derivative is slope is 4. Let's condense this a bit. Negative 2 minus 1 will give me a negative 3 exponent. A negative 2 times 4 is a negative 8 coefficient. So I'll have negative 8, and then inside of parentheses 4x plus 7, close the parentheses, all to the negative third power. One more example. It's a little more challenging. G of x equals 1 over parentheses x squared minus 5x to the power of 3. Well, we could just rewrite that as x squared minus 5x to the negative 3. The fact that we have a 1 here in the numerator is helpful, that it doesn't have to be a weird quotient. There's no variable going on. Let's just rewrite it and simplify. Instead of 1 over to the power 3, we have a function to the negative 3. I can identify the inside of the parentheses as x squared minus 5x. The outside is to the negative 3 power. So when I take the derivative of the outside, I bring the negative 3 down, leave the parentheses, that's like where my variable goes, and I subtract 1 from the exponent. This is a generalized power rule. But in the chain rule, the something that we leave alone is the inside function, x squared minus 5x, exactly as it was. And then we multiply by the derivative of the inside. The derivative of x squared is 2x. The derivative of minus 5x is a minus 5. I now have minus 3 coefficient. And then I move this 2x minus 5 up front. I kept it in parentheses, so everything still multiplies okay. But with an exponent of negative 4, I move the x squared minus 5x to the negative 4 to the back, just so that this negative 4 had breathing room. This function starts with all positive exponents, so we should rewrite our answer with all positive exponents. Negative 3 is good, no negative exponents. 2x minus 5 is good, no negative exponents. The negative 4 is only on the x squared minus 5x, so only the x squared minus 5x gets moved to the denominator, and the exponent becomes positive. Anytime you cross a fraction bar, your exponent changes sign. All right, the chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside. Let's do more. G of x equals 3 over 7x minus 9, all to the power of 5. So here's what I did. I rewrote this, and it looks like oh, no, we're good. So the 3 is good. I don't want to use a fraction, or I don't want to use a quotient rule here, because a quotient rule with the chain rule, this just gets to be a lot after a while. If I can avoid it, I will. I can rewrite so this entire denominator comes up across the fraction bar and gets an exponent of negative 5. Now, in black, to find the derivative, in black, I have the constant multiple rule. 3 times this stuff. If I want to find the derivative, it's 3 times the derivative stuff. Awesome. Leave the 3 alone. Now we can focus on just this portion. Inside is 7x minus 9. Outside is to the negative 5 power. Alternatively, you could call this the outside, and it'll get you the exact same spot. Okay. Here we go. So derivative of the outside, the negative 5 parentheses, subtract 1 from the exponent, leave the inside alone, 7x minus 9, and then multiply by the derivative of the inside. The derivative of 7x minus 9 is, of course, its slope of 7. So we're going to take negative 5 minus 1 to get an exponent of negative 6 on the 7x minus 9. What about our numbers? We have 3 and negative 5. That's a negative 15. A negative 15 times 7 is a negative 105. Negative 105 times 7x minus 9 in parentheses to the negative 6. Or we can rewrite it again with the positive exponent, negative 105, over parentheses 7x minus 9. Close the parentheses to the 6th power. Over and over and over again, it's always the same thing. To find the quotient of r of x equals 0.1x minus 4.2x to the negative 1, all to the 0.5, I identify my inside portion here in blue, and my outside portion is 0 to the power of 0.5. The derivative of to the power of 0.5 is 0.5 to the power of 0.5 minus 1. To the derivative of the outside here in green, leave the inside alone exactly as it's written, exactly the same. And then we multiply by the derivative of the inside. Find each derivative. Now, and I did the derivative in steps here because I'll clean it up down here. Simplification, always a great idea later. I needed to simplify my exponent here. Why not take the time to simplify the derivative as well? Now, sometimes you cannot avoid the multiple use of rules, derivative rules, product, quotient, and chain rule. In problem number 7, I see that s of x is the cube of the fraction 3x minus 9 over 2x plus 4. Now, I look at this and I definitely see 3x minus 9 over 2x plus 4 is just screaming, hey, look, I have a fraction. But also, this fraction is inside of something. What is it inside of? It's inside of a third power. So the inside is a fraction. All right, so what? We'll deal with it. The outside is to the third power. So I know that at some point, I'm going to need the derivative of the inside. So I'm looking here at a low value of 2x plus 4 and a high value of 3x minus 9. I have to use the quotient rule inside of my chain rule. The quotient rule says low, 2x plus 4, d high, so derivative of 3x minus 9 is 3, minus high, 3x minus 9, d low, the derivative of 2x plus 4 is 2, all over low squared. And then because I'm going to use it, because I'm going to put something that in somewhere else, I have to simplify it. 2x plus 4 times 3 is 6x plus 12, minus 3x times 2 is a 6x, negative 9 times 2 is a negative 18, but with the negative here also, it becomes a positive 18. I'm going to leave low as squared. Check it out. 6x's cancel. 12 and 18 makes 30. So the derivative of my inside is over here. And now I have an inside and outside. And I have my derivative of the inside. That's all I need for the chain rule. Derivative of something cubed is 3 times something squared. 3 minus 1. What is that something? Leave that inside alone. That's your something. And then multiply by the derivative of the inside, which we did. And then I just tighten it up. The only characters I changed here was I called 3 minus 1 2 instead of 3 minus 1. And yeah, you don't have to go any further. You don't have to combine to make these a common denominator. You can leave it like this, and I'm okay. We're finding derivatives here. If you're going to use it, simplify it. If you're not using it for anything else, don't bother. All right, that's how you lose your mind. Number 8, g of x equals x squared plus 3x, all to the negative 2 power, times 5x cubed plus 2. Oh, I said the word times as I was reading it, which tells me I'm going to have a product rule. With the product rule, I'm going to look at first and second, and derivative of the first and the derivative of the second. So, product rule, I have first derivative of the second plus second derivative of the first. Those are the words I usually use. The first is x squared plus 3x to the negative 2. The second is 5x cubed plus 2. Derivative of the second, super easy, comparatively. Because the derivative of the first, now I have to use the chain rule inside the product rule. So as I'm looking at this, I have my inside of x squared plus 3x. My outside is to the negative 2 power. So to find the derivative of the first, it's a derivative of the outside, so negative 2 to the power of negative 3. Leave the inside alone, so I leave the x squared plus 3x inside. And then I multiply by the derivative of the inside, which is 2x plus 3. So I found my first, my derivative of first, using the chain rule. My second, my derivative of the second. We could put these together, and we have first multiplied by the derivative of the second plus second times the derivative of the first, which we use the chain rule to find. All right, I know, my mouth's just about over it too. But wait, there's more. Let's talk about a word problem. Word problems really are the most important part of mathematics. We use math to describe the world around us. We use words to make those observations. And we got to connect them with math. This is the whole reason we math, is words. So let's look at Paramount Electronics. They have an annual profit given by capital P equals negative 100,000 plus 5,000 Q minus 0.25 Q squared, where Q is the number of laptop computers it sells each year. All right, so their profit depends on the number of laptops it sells. Awesome. Now, the number of laptop computers it can make and sell each year depends on the number of electrical engineers that Paramount employs, according to the equation Q equals 30N plus 0.1 N squared. All right, so we have a formula for profit given in terms of Q, the number of laptops sold. We know all about Q, the number of laptops sold, based on N, the number of engineers. We want to use the chain rule to find the derivative of P with respect to N at the moment when N equals 10. All right, so evaluated at, or when, that's what this line means, and interpret the result. Now, we know that P is a function of Q. And we know over here that Q is a function of N. So if these really were fractions, which they're not, so I'm going to use yellow, it certainly looks like those DQs might cancel out. Man, now I want Dairy Queen. It looks like we're going to get dP/dN, the value we requested. And that's exactly right. Okay, and I have it written here. Yes, I want you to watch it dynamically. These are not fractions, but they behave similar to it. So here's what I'm going to do. I'm going to find the derivative of profit where Q is my variable, dP dQ. So I'm going to d dQ and write the profit equation. So instead of the P, I just wrote the profit equation. Now this tells me it takes the derivative where Q is my variable. Derivative of negative 100,000 is 0. Constant term, 0. 5,000 times variable, 5,000 Q has slope of 5,000, minus 0.25, so we'll leave the minus 0.25. The derivative of Q squared is 2Q. And when I simplify, I'll have 5,000 minus 0.5Q. All right, so that's dP dQ. We also have dQ dN. Well, that's the derivative with respect to n of my Q function, right? My Q function. When n is the variable now, right? Q is the variable here, n is the variable here. Derivative of 30n is 30. The derivative of 0.1n squared is 0.1 times 2n, and that's 30 plus 0.2n. Okay, but we agree, right? You didn't admit it because you're not here while I'm recording, but trust me, you agree. dP dN is dP dQ times dQ dN. So I found dP dQ, that's 5,000 minus 0.5Q. And I found dQ dN, that's 30 times 0.2N. Awesome. But what about the N equals 10, right? The N equals 10 that we have here. We have a value for N, but we don't have a value for Q. But don't forget, we have a formula for Q up here. Q of 10 is just 30 times 10 plus 0.1 times 10 squared. So that's 300 plus 10 squared is 100. A tenth of 100 is 10. So that's 310. So now dP dN evaluated when n equals 10. I know when n equals 10, Q equals 310. So I use Q equals 310 when n equals 10, and I can evaluate to find 155,040. But what does this represent, right? Sure, we could find this number. Great. It's got like 6 digits. Cool. What's it mean? Well, what it means is right? DPDN, it's the change in profit per engineer. N is what's changing, so the change in profit per engineer. DPDN evaluated at N equals 10 equals 155,040 means that for 10 engineers, the company's profit will increase, because it's positive, $155,040 per electrical engineer. Wow. And that happens to be when they're making 310 laptops, making and selling. All right, that's it for the chain rule. Inside, outside. If you can do composition of functions, which I know you can, then you can also do chain rule. Thanks for listening.